Okay, so a couple things to start off with. At least we have a much fuller class today. Most of you are, I assume, in the CCE class. They had the thing. How was that? Was it good? No, was it? Were there other speakers? I wonder why they had it. It was downtown, right? Oh, I heard it was in downtown Milwaukee. Okay. Well, my follow-up question was going to be, why is it that it's downtown when if he's the only speaker, why didn't we have it somewhere here? Okay. Well, at least you didn't have to like get bussed down there or something. So you would have rather been in this exciting class, obviously. All right. Oh, I think you might have left a book in my. Did you leave a planner or something in my office yesterday? Okay, well, it's sitting on the table. It's always open, so just whenever you pass by, just go in and grab it. Okay, so some of you maybe have seen some of the upper class computer science people walking around with bracelets on. So we are starting a tradition kind of like karate or any other martial art where we're going to hand out belts for your current skill level in the art of computer programming. And as all starting, when you start out, you become white belts. We're going to hand out white belts today. When you complete this class, you will become a yellow belt. So you'll start the second programming class, CSC200, as a yellow belt. When you complete that class, you'll start the third class, CSC300, as an orange belt. When you complete that, you'll be a green belt. From that point forward, you start differentiating yourself based on merit from your classmates. So you might have a classmate that's sitting next to you that is better than you at programming, one that's worse than you at programming, so then you can make fun of them or whatever, in, of course, a Christian way. Gretchen in the cafeteria knows all about this, so she might like refer to you as white belt or yellow belt or something like that. But in any case, this is the inspiration for this is this Hulu movie that I saw recently called The Art of Self-Defense. It's absolutely hilarious. So if you have Hulu, I recommend you watch that movie. One of these days, maybe next week, Blaine Andrade and I were talking about it. Maybe Monday or Tuesday next week, we might set up a movie night here in the department where we just watch it. But in any case, that's the scoop. So I'm going to hand these out. I'm actually just going to barely open it, and then I'm going to pass around the thing because there's like a plastic thing inside. So pass these around, snake them throughout the whole. Everybody grab one white belt. Got to wear it at all times. We're going to call you out in the hallway and all that stuff. So there's a couple ways of earning stripes. So you can earn a stripe on your belt if you're a regular attendee of Front Row Club in Chapel or a regular attendee of the Tuesday Bible study. Today we actually spilled over to a second pew at the Front Row Club at Chapel. We got Pastor Doug up there today. So we're trying to get 30 plus computer science students sitting in the front row of Chapel, really fill it out, maybe even spill into the second row. I think that would be a pretty cool thing. But in any case, those are some ways you can earn stripes. There's going to be some other ways, maybe attending a hackathon, stuff like that, so you can get some extra stuff on your belts. All right. So when you get your belt, make sure you put it on. Doesn't matter which wrist you put it on. Your only excuse for not wearing it is something like if you have like an allergy to rubber or something like that, then don't harm yourself. But if you just don't think it looks good, bad excuse. The points trickle off your grade like a bleed effect. So it's like 1 point per second or something like that. So it'll be bad. All right. So that's going to create a little competition within the department post the third programming class. But in here, everybody will be white belts until we graduate to yellow belts. All right, questions about any of that game? All right, so let's continue on talking about job. I think our third and final paper is due on Friday, if I looked correctly, right? Okay, so last time we were talking about kind of the evolution of our operating systems. We talked a little bit about the Apple versus Microsoft thing and the war with, we talked about Bill Gates and his thing with giving the licensing DOS to IBM when he didn't even have an operating system. Last time we talked about Apple firing Steve Jobs. He leaves Apple, goes and creates another company called Next Computers. And what we have today is, with Apple, is we have an Apple logo sitting on top of Next Computers. So what's under the hood here, what's the various software things, these are all Next Computer stuff. So we talked about Mac OS X being our Unix-based. Thanks. Everybody got one? All right, so being our Unix-based version of Mac OS X, and actually Apple dodged 2 bullets there. So one of the bullets was they switched from their traditional OS 9. So all of these operating systems were based on top of Apple's old operating system model, which used something called preemptive multitasking, which really didn't let you run more than one program at once effectively. So it was convenient if you had to switch back and forth between maybe your email, or email might even be a bad example, maybe a web browser that you aren't expecting it to do anything in the background, and a word processor. But if you had like a download going or something like that in the background, preemptive multitasking would make that download go very, very, very slow. So it wasn't actually running in the background. It more or less gave you a convenient way of flipping between applications. We talked about a similar thing with iOS versus Android. So everybody in here today is either probably running iOS or Android for your smartphone. If you have an older phone, maybe you're on BlackBerry or Windows Mobile or something like that. But chances are it's about a 50-50 split between iPhone and Android. Out of curiosity, since we have a bigger group today, how many of you are on iPhone in here of some sort? Okay, and who's on Android? Okay, I think maybe actually the iPhones have it by a little bit in here. So I assume the iPhone folks think iPhone's better, and the Android folks either think Android's better or they hate Apple. One of those two, right? Okay, one of those two things. Well, I got news for you. Apple's a big company, and just like every other big company, they're going to have some evil practices, so just deal. Reality today. Shut up! He didn't even flinch. It was good. It's bonus points today. All right, so reality is today, iOS and Android, let's call them legit competitors. Who's the best? Probably whichever one had the most recent release. There are things that iPhone wishes they had from Android. iPhone users wish that they had maybe on that Android people have, and vice versa. So it's, you decide. Really, Apple today is solving the Apple problem from the old Apple Microsoft war days. That is, they're writing software, iOS, for their own hardware, the iPhone, right? So they make the hardware, they make the software. It's not necessarily surprising that their software runs pretty well on the hardware. In fact, it should actually be kind of surprising when they do have some of the problems that they have, because they only have to test it on like 6 devices, right? Because they don't really care whether their latest, greatest version of the software runs it on the iPhone 6, right? Because if it doesn't, what does that make you do? It makes you go and buy an iPhone 7 or an 8 or an iPhone X10, whatever you want to call it. Punchline is Apple will keep taking your money. So they want the software to work on those older devices so far as you are not ticked off, but they want to keep you happy enough that when you finally replace it, you give them more money for the newer device. It's the Apple way, right? Nothing wrong with that. Android, on the other hand, is solving the old Microsoft problem. They're writing software that's running on a whole bunch of different people's hardware, right? So those of you who are Android users in here, maybe some of you are running, how many of you are running one of the Pixel phones? Anybody in here with a Pixel phone? Okay, so one person is running the what's officially considered Google's phone, even though they outsourced the development of it to another company. But let's just say that's Google's phone. Google writes that software for that phone first, so when they release their newest version of Android, day one it's available on the Pixel phones. So if you always want to be running the latest, greatest, coolest version of Android, get a Pixel phone. Great phones, people love the Pixels, nothing wrong with it. We'll call it one of the Android flagship phones. How many of you are running a Samsung Android device? All right, so that would be another one of our flagship phones. So those of you so this is a Samsung Note 10 Plus. So my wife runs an iPhone X2. So, she's iPhone, I'm Android, I write software for both, so we have development devices in the family. Punchline is that, even though this is the latest, greatest phone from Samsung, I'm technically not running the newest release of Android. It's not available for this yet. Samsung has to go through and add the extra crap they want to add to it. Samsungify it, add Bixby, so some of those things. And then they'll release a buggy OS for it, so everybody will be happy. So I have my Android phone set up to reboot literally every single night at like 3 a.m. or something like that. So I wake up with a fresh boot and things seem to just work. It's great. But in any case, Android is solving the old Microsoft problem where they're writing software meant to run on a whole bunch of other people's hardware. And also given the fact that Android is an open source product. What does open source mean? When I say that software is open source, what am I talking about? Go ahead. Okay, you can go in and see the source code. You could also modify the source code, right? You might not necessarily be able to contribute to the core project. You can't go in and, unless they've invited you in as a contributor, you can't update the next release of Android. But you can certainly take the current release of Android and make modifications to it and build it for your own hardware, for your Android machine, and have a version of Android that isn't the release version of Android. And that's what companies like Samsung and Motorola or LG, that's what these guys do to create a modified version of their of the Android operating system. Some modify it more or less than others, but to run on their particular stuff. So with that in mind, Android is solving the old Microsoft problem, which is either we can say it's a good or bad thing, but generally speaking, it's probably fair to say today that Android runs better than it should run, given that it's running on a whole bunch of different hardware. It's got to support these different cameras. Every single time a new phone comes out, they talk about how our camera is up to 20% better than last year's camera from so-and-so. It's, really what are they talking about? They're talking about like a very, very, very specific use case. When you're in like medium light situations and you're outdoors and it's like less than 0 degrees Fahrenheit and it performs better in that situation. Then they can say stuff like it's up to so much faster. Same thing with the processors. Whenever you buy a new laptop or something like that and they say we have a, this year's Core i7 processor is up to 50% faster than last year's. We'll pretty soon here talk about how processors actually work when we start talking about compilers and interpreters and programming languages. But, this year's processor has maybe one little new component on it that's made for a very, 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 very specific problem. And maybe it's up to 50% faster for that one little tiny use case that hardly ever happens. But because it does it's possible for it to happen, they can claim it's up to 50% faster, that kind of thing. So beware of claims like that because they may not actually impact you as the end user. All right. So we talked about some of the differences between Android and iOS over the years. So now we are at this point in our evolution of our languages where we're at Java. All right. So We've seen our jump from C to C++. This was procedural language compared to object-oriented language. Microsoft chose the C++ side. Apple went with this language called Objective-C. We can just relatively call them equivalents. They're just not the same language because they hated each other. And if Microsoft's going one direction, they're going to go the other direction, and life goes on. All right, but now we're going to look at Java. What did Java do? So, we have our C language. This was procedural. Somewhere in here I have C++. So C++ was an object-oriented version of C. We're going to add to this, and we're going to say this guy empowered the programmer to make, quote, bad decisions. And what I mean by that, and I'll throw one more thing here. So C++ as well as C gave the programmer complete control over memory, computer memory. All right, we're not going to go that far into that right now, but at some point I'll give you an example of that. And most programmers, I want to say beginning programmers, but really even advanced programmers, so let's call it green belts and below. We'll just have to start integrating the colors into our examples, are going to be very intimidated by memory inside of our computers because memory addresses are scary looking. They're big hexadecimal base 16 numbers that look very, very scary. So you might see a memory address that looks like, 0x13AB2C45F, something like that. And at a glance, that's scary, right? Now, I promise this guy converts to a base 10 number that we will recognize, but will be equally scary. Okay, so one of those numbers that's like super long and you have to go through and do the little, count by threes to figure out how to say it. And then you might even have to look it up and say, well, is this quintillion or quadrillion or all that stuff. So you might not even be able to pronounce the number without a couple of Google searches, right? But in any case, it's just the number. Our computer's memory is like, when we think about computer addresses, memory addresses, the computer's memory is like one big long street. And every single house in the entire world, in our entire computer, is on that one street. So if you want to go to house number 4, you go to house 4. You want to go to house 4 quintillion, you go to house 4 quintillion. Go ahead.
Is that like an address for like a single bit?
Why would the address of a value? Let's keep it at that for right now. So it could be a number. Probably not for a single bit. It would usually be byte addresses. So 8-bit chunks. We'll talk more about that at a later time. But for right now, keep the abstraction at this level of every place in memory, every value in memory is like a house in the real world, and all the houses are on one big long street. So it's house number 1, 2, 3, 4, 5, 4 quintillion, so on and so forth. That's a pretty easy way of addressing, isn't it? You might not like it if you have to deliver a letter to a house way down the street, okay? But it is pretty easy to get to that long, the house way down there. You just have to start counting houses, and we can do that. Our real life example of addresses is far more complex than computer addresses, yet those don't intimidate us because we're used to dealing with them, right? We have a house number, we have a street number, we have a city, we have a state, we have a country. You have all these pieces of information that ultimately zero you in to an actual value, a house, somewhere on the planet. That make sense? So human-based computer addresses, human-based addresses are way more complex than computer-based addresses, but we've been using them our whole lives, right? Remember, I don't know, what is it, in first grade or something like that? You have to, or maybe it's in kindergarten, that you learn you have to learn your phone number, your address, and shoe size, whatever it is. You have to do all that stuff. But we've been using human-based addresses our whole lives, so we're comfortable with this very, very, very complex address system, right? Except now we're not all that complex with the extra zip code stuff, right? The dash with like the extra numbers, like we don't care about that, right? if you copy and paste the zip code from someplace, you might put it in there. Otherwise, the zip code is 53097. That's what it is. I don't care what borough or whatever of something that we have the extension on the zip code. But we're comfortable with human-based addresses because we've been using them so long. I'm telling you that computer-based addresses are far simpler. We usually see them as a hexadecimal value because our computer memory gets very large. Those of you out here, you have 4 gigabytes of memory, 8 gigabytes of memory. Anybody have 16 gigabytes of memory? 32 gigabytes of memory? A half a person has 32 gigs of RAM? 64 gigs of RAM? Nobody with 64? So, huh?
That's a lot.
It's a 60.
What? A lot. Like, you read Apple's like Mac Pro that has like up to 1.5 terabytes of RAM.
Servers might have that. Yeah.
Like your Mac Pro that up to.
Right, because you're running it as a server and you're sharing system resources. So like this computer here, I run a lot of virtual machines. So this computer here has 64 gigs of RAM in it. Now, under a single operating system, if I'm just running Mac OS, I'm not going to be using 64 gigs of RAM. Realistically speaking, I'm not going to be using 8 gigs of RAM, right? So anything over 8 is probably overkill for a single operating system. 16 would give you some comfort, some wiggle room. But I virtualize lots of operating systems. I have Windows on here too. So because of that, I can have multiple things running at once, yet still be able to flip back to the Mac OS and have it running at full speed, and be able to utilize, I'm splitting my system resources. I have a single container here that has a bunch of different resources in it that I'm splitting between multiple operating systems. If I wasn't doing that, I'd have a whole bunch of resources in this computer that just sit there dormant, completely unused. Because I'm not going to be able to use 64 gigs of RAM just on the Mac OS unless I'm doing something very specialized, rendering an animation or something like that. Some very specific task that you might do once in a blue moon unless it's your profession. Okay, so in any case, C++ empowers the programmers to make bad decisions. I'm going to talk about that here in a second. And programmers have control over memory, and memory looks scary in computers, but it's actually easy. One house right after another, all on one big long street. All right? Well, as you go through your computer science education here, we'll zero into more details. In that when you take the 325 class with me, which is computer organization and architecture, we only talk about those details. So you'll get the punchline eventually, but for us right here, we don't have to worry about it too much. We just want to know that it exists. All right, and what I mean by that empowers the programmer to make a bad decision. Let's say one of you is having a party tonight, and you're going to invite your new best friend Mike to your party. Obviously, right? I'm a cool enough guy. Well, we decided better than Pat Ferry's speech. This is more entertaining. Maybe not. We have a couple sleepers, I think. But in any case, you're inviting me to your party. Do you hand me your house and tell me to open the door at 8 p.m.? Or do you give me the address where your house lives? Or I can go find your house. Which do you do in real life? You might have the one or two smart asses that say, oh, I'll give you the house, right? You're going to give me the address. You're going to tell me where I can find the house, right? And then I drive there. And as human beings, when we start talking about algorithms, we can fill in the blanks. You don't have to give me great directions. But if you just give me the address where I can find the house, I can put it into Google Maps or whatever, and it'll get me there, right? So you'll give me the address for the house. Why won't you give me the house? It's heavy. It's big. It doesn't make any sense to hand somebody the house, right? Now remember, computer programming languages, their job is to allow human beings to solve problems in a similar way to how we already solve problems. We don't solve problems in real life by handing people the house. We tell them where they can find the house in memory, right? Find the house somewhere in the world. C++ allows the programmer to choose to hand somebody the house. Now, back then, in the days where C++ was commonly used, this would have been problematic for, green belts and below, because they are going to be more prone to not understanding memory, making mistakes, things like that, having syntax that ends up working, but they don't necessarily know why it works. And we didn't have as much memory as we have today. Today, if we have an object that represents a house, I don't know, I'm just going to make up a number. Let's say it's 64 kilobytes of memory. Just pulling that out of the sky. That's a very, very, very small amount of memory relative to what you have inside your computer. So with that in mind, who cares? Here's the house. You're wasting some memory, but I had extra memory to work with. Doesn't matter. But back in the days when C++ was, heavily used, we didn't have 64, 32, 16 gigabytes of RAM. We had 64K of RAM, or 256K of RAM, or 8 megabytes of RAM would have been considered a hefty computer back then. 8 megabytes. What's our breakdown? So if I come here right before Java, let's call this memory sizes. We have a bit. What's a bit? A single 0 or 1? That's what a bit is. Now over here on the, we have something called a byte. A byte is how many bits? 8 bits. So a byte is a collection of 8 bits. So then from bit, we have kilobit, lowercase b. A kilobit is, anybody know how many bits are in a kilobit? I hear like a lot of whispers. Let's increase that. 64? It's going to be 1,024 bits, or in 1 kilobit. It's going to be a very important multiplier for us here in a second. A megabit, lowercase b, I'm going to swing back into this here in a second, is 1,024 kilobits. Gigabit is 1,024 megabits. That's probably as far as we actually use today, but I'll go ahead and throw one more on there just because that's we're going to have the equal thing on the other side. We could say a terabit is 1,024 gigabits. Now we're over here on the byte side. A kilobyte, big B. So notice kilobit versus kilobyte. Major, major, major difference by a multiplier of 8. A kilobyte has 1,024 bytes. A megabyte, big B, has 1,024 kilobytes. A gigabyte, big B, has 1,024 megabytes. A terabyte, big B, has 1,024 gigabytes. So now when you hear these values used in real life, you want to make sure you know which of these columns we're in. So a common thing is, how many of you have internet at home? Most of us, right? How many of you know how fast your internet is at home, or at least what you're paying for? All right, so every computer science person should know what their speed of internet is at home. So a couple of you rose your hand out. What's your speed of internet at home? Go ahead.
It's around 1,000 megabits.
Okay, good. 1,000 megabits, or so you're paying for gigabit internet through his provider. A lot of times you'll see the commercial for internet, and they'll say, "Oh, it's it's 200 meg internet," right? They'll leave the rest of the part off as an advertising thing, and you might think, "Oh, well, they're talking about megabytes. I can get 2,000 megabytes of maximum download speed." It's megabits per second when we talk about our internet connection. So internet, kind of a common starter speed today for, let's call it like a Milwaukee type town, might be 200 megabits per second, lowercase b. All right, so this actually means that if you wanted to download something, you could expect to be able to get a maximum download speed of 25 megabytes per second. See how that works? It's you're divided by 8 to get from this column over here, megabits, over to this column here of megabytes, because this is a multiplier of 8 bits, or 8 bits is 1 byte. Make sense? All right, so important conversion stuff. Similarly, if you get 1 gigabit per second internet, which is equivalent to 1,024 megabit per second internet. Okay, so he had said roughly 1,000 megabits per second, so he was in the right ballpark at least. Okay, so he has gigabit per second internet, which is the equivalent to 1,024 megabits per second, which is 1,024 divided by 8, which should be 128, I think. No, 128. That's 128 megabytes per second. That's the maximum theoretical download speed he gets. Now, on his internet, you don't very often get 128 megabytes per second download when you're trying to download something. Why not? You're paying for it.
Because they recently changed that law so they can actually fluctuate the internet speed if they want to.
Okay, there's probably some truth to that under the hood, but let's say they're not fluctuating it. You get your maximum bandwidth. You're still not going to get 128 megabytes per second very often. Why?
Depends on the location of where you're trying to download it from.
Okay, not just the location. Go ahead.
Sharing it with others.
Cable modems, you are sharing your bandwidth with others, that's true. But let's say there was enough to go around. Today, there pretty much is. That sharing issue isn't so much of an issue.
Because your computer's using it for other resources?
Potentially. That's one potential thing. Go ahead.
My thoughts were that if it were to download at that speed, there may be some data that gets corrupted at that kind of speed.
Historically, that would have been true. Today, we have something called TCP/IP, which kind of protects us against that. Go ahead.
So maybe the medium you're using to get the internet, like your Wi-Fi doesn't allow for 120.
Okay, so that's something we do need to start thinking about is, whether we might have fast enough internet. Technically, think of the internet like your water supply. Okay, you might have water that could come to your house and pump out at, let's just make them another 50 gallons per minute. But maybe the little hole you have in the sink won't let it come into the house that quickly. Something like that. Certainly a possibility. Okay, still not necessarily the reality. The reality here is our download speed is someone else's upload speed. When you get your internet, when you have your 1 gigabit per second internet, it's more than likely 1 gigabit per second down by, I'm just going to make something up, 120 megabits per second up. This is called asynchronous internet or asynchronous connection. The download speed and the upload speed are not the same. This is okay for us as consumers. As consumers, we download way more often than we upload. When are we uploading? When we're attaching a Word document to an email, something like that. Every now and then, we might be uploading to some server or something like that, putting something on Dropbox or one of these things, but that's something that's kind of happening in the background that we're not necessarily paying attention to. So consumer internet, the download speed is faster than the upload speed because the download speed is what we care about, right? All right, so, but when we're downloading something, we're at the mercy of the upload speed of where we're downloading it from. He mentioned location in the world. That possibly is one of the driving forces, right? When we are downloading something from Russia, let's say, There's a lot of different hops we have to go through on through the internet in order to ultimately get to that computer that's sitting in Russia. So not only are we at the mercy of how fast that computer in Russia can give us data, we're also at the mercy of all the little hops that it has to go through to get to us, and the speed of those individual networks and those types of things. All right. And then again, we said something about sharing data. We're sharing it among multiple people. Well, that upload speed from that computer in Russia, if there's 10 people downloading from there at the same time, that is being split 10 different ways, whatever their maximum upload speed is. A lot of times servers are on synchronous internet, so their upload and download speed would be the same. Like here on campus, our web server and stuff like that is synchronous. So whatever our total pipe is, that goes both ways. But point is that commonly our maximum download speed for consumer internet is greater than the speed that the source is going to be able to give us the data. So does that mean we're wasting our money on gigabit per second internet or 768 megabit per second internet? Just bragging rights? What do you think? Okay, somebody over here gave the answer about sharing, right? So we're sharing that data. Go ahead. Oh, you're stretching. So, if you're in an apartment or you're a family of 4 or something like that, where you might be streaming Netflix downstairs, somebody else is streaming Netflix upstairs, you got somebody playing some video games, you're using your internet in 4 or 5 different ways at once in your house, right? And now we have Amazon Echoes all over the place, and smart refrigerators, smart toasters, smart wristwatches, whatever. We have smart everything now, right? So each one of those is using a little bit of our internet at all times. So we need to have enough internet coming into our house, enough bandwidth. This goes back to our water example, right? We need to have a strong enough flow of water to our house that somebody can take a shower downstairs, take a shower upstairs, and still wash their hands in the kitchen. Make sense? Internet's kind of the same thing. So we need enough of a supply to give us all of our needs in, let's call it, a worst case situation. All right, make some sense? And you've probably been in some places before. Maybe you even live in a place where you do have that problem, where if you're in one area and somebody starts washing their hands, you're in the shower, somebody starts washing their hands, your water pressure drops, right? Because now it's being split between 2 different places. Or somebody turns something else on and you get cold water, right? Because your hot water heater, that tank, only has so much hot water in it. So when somebody else is starting to share that, it might not be able to keep up, something like that. All right, so that water example is very similar to our internet example, where we want enough for our needs. Now, there probably is a such thing as too much, right? By today's measurement, a gigabit per second is probably more than most people who aren't running BitTorrent would use. We'll talk about BitTorrent at some point. I'm sure most of you have at least heard of torrent files. Plenty of legitimate uses for it, but most of the uses are not necessarily legitimate, but whatever, it's a deal. Well, let me just give you the 30-second version of it. BitTorrent downloads are the goal, are meant to combat what we just talked about. So what BitTorrent does is it says, here's this file you want to download. We're going to have 200 people who all have that file. You're going to download a little bit from this person, a little bit from this person, a little bit from this person. All of a sudden, you benefit from that person's upload plus this person's uploads from this person's upload, which allows you to maybe get closer to your maximum download speed, because you're downloading parts of that file from multiple sources. Make sense? That's the idea behind BitTorrent. I'm not reliant on that one computer in Russia's upload speed. I'm reliant on her upload speed plus his upload speed plus his upload speed, yada, yada, yada. Divided by the number of people that are downloading the part of the file from her, the part of the file from him, and the part of the file from him. So the more people who are seeding the file in BitTorrent, the better we can likely expect our download speed to be, right? But we're usually poor users of BitTorrent, right? As soon as we're done downloading, we stop seeding, and we're not sharing. we got our illegal movie, so now let's go ahead and get out of Dodge so we don't get caught, right? What's the saying for BitTorrent users? Always use a VPN. So look around, anybody whose eyes just got a little shifty, they're probably using BitTorrent for purposes that would not necessarily be in line with Concordia's values. But it is what it is. That's what technology does for us. It exaggerates what's already in our hearts. All right, so the idea is this is kind of how internet works. This is how data sizes work, which is more important for us here. Because when we deal with computer programming and we deal with computers in general, having an understanding of bits versus bytes is a requisite. We need to have that understanding. All right, so we're going to cover this. We're even going to write programs that do some conversion between these. So we mentioned earlier that one of the things that Java does, well, we mentioned a problem with C++ being it empowers the programmer to make poor decisions, specifically as it relates to memory. And we talked about this example of houses. You invite me to your party, do you hand me the house or do you hand me the address to where the house is? Well, the house is heavy. It's going to be lots of kilobytes, megabytes, whatever. All right, it's going to weigh a lot, whereas it's going to be a big file. Whereas an address is going to be relatively small. Think of it kind of like writing something down on a Post-it note and handing somebody the Post-it note. Now, every address will be the same size, but it's something you can kind of put in your pocket, right? Okay, so depending on the type of operating system you're on, we have 32-bit operating systems, 64-bit operating systems. So let's say you're dealing with a 64-bit operating system. More than likely, the address size will be 64 bits or 8 bytes. 64 divided by 8 bytes. Relatively small, right? Relatively, that's a, kind of a medium-sized Post-it note. Always, always, always going to be smaller than a house, even those tiny homes. Make sense? All right, so it's always going to make sense for you to hand me that Post-it note with the address of your house and tell me to be there at 8 p.m. than it would be for you to hand me the house. Again, programming languages are built to help human beings solve problems in the ways that we already solve them. With that in mind, it would never make sense in human problem solving for us to hand somebody the house. But C++ allows the programmer to make that decision. Now, sometimes very advanced programmers, let's call them purple belts or higher, might be able to leverage the memory to do some interesting things. So having that control over memory may be beneficial. So we don't want to talk about it as a bad thing necessarily. We really want to talk about it as kind of a dangerous thing. And maybe something that beginner programmers don't necessarily have full control over yet. With that in mind, a language like Java takes that decision making away. So takes the decision away from the programmer in how to deal with memory. All right. Now, a lot of textbooks would say something along the lines of Java does not have something called a pointer. Anybody know what a pointer is? Anybody who's had maybe some programming before? So a pointer is a variable type. So we talked about how do human beings solve problems, memory, asking questions, repetition. 100% of programming languages have facilities for those three things. Memory is usually done through variables. How do we remember stuff in a computer program? So a pointer is a variable type capable of holding a memory address. This isn't any different than an integer being a variable type capable of holding a number. Okay, it's just a value. And a lot of textbooks for Java will claim that they cannot deal with that pointers don't exist in Java. Well, in our last couple minutes here, let me show you an example as we're transitioning, starting to transition towards the programming stuff. So I'll go ahead and get Raspbian started on my computer here. And I think I have the Java compiler on here, don't I? Yep. All right, so I'm just going to write a quick little Java program we'll just write a quick little Java program. So we'll call this guy test.java. Oh, I already have something in here. Good. I already have this example in here. All right, so forget about the syntax here. We're going to see this again, but I'm going to create this variable type called an array. So this is an integer array called AR, and it's capable of holding 10 integers. We'll talk about that plenty later on. I'm also creating another object here of type random called R. I'm going to go ahead and, well, it doesn't matter which of these we print out. I'll compile this guy, which we'll talk about what compilers are. And then I'll run this guy, and we get crazy looking memory address. Pointers exist in Java. All right, pointers exist in Python. We just don't have a special syntax for controlling them ourselves in either of those languages. All right, they exist, but they're making those decisions for us. Java and Python, they decide whether the house gets passed by value, here's the actual house, or if that house gets passed by address, here's the post-it note where you can find that house. All right, those languages make those decisions for us. So Java, in reality, does not have a, and we can kind of say Java/Python, does not have a syntax for directly working with memory, whereas C++ does. C does. So in those languages, the programmer is empowered to make those decisions. Now, you've heard me mention this thing called a compiler several times. I think I have the three kinds of programming languages: functional, procedural, object-oriented, and we focus on the procedural versus object-oriented languages. So we talked about the procedural versus object-oriented telephone. I'm now going to create another slide here called there are three kinds of programming languages. So we're kind of looking at languages through a couple different lenses. We have machine language. We have low-level languages. We have high-level languages. What language does our computer speak? Binary. Zeros and ones. Now, how many of you want to spend your days with a little 2-button keyboard just tapping out programs? We would go crazy, right? And that's not for human consumption. Low-level languages have a one-to-one relationship with the CPU. And we'll start talking about the CPU at the beginning of next class. High-level languages have a one-to-many relationship with the CPU. So we would call this guy a power tool. This is a manual tool. This guy is not for human consumption. Okay, we don't want to deal with it at the atomic level. We will, in a pinch, use a manual screwdriver to solve some problems, but human beings really prefer the power drill, right? We want power tools to do our bidding. So our high-level languages are going to be languages like Python, like Java, yada, yada, yada. These are our power tool type languages. Low-level languages are going to be like a language called assembly, which we'll talk about next time. Machine language, we already said, is zeros and ones. So we're going to start off next class talking about the nature of the CPU. What actually is a CPU to give meaning to this idea of one low-level languages having a one-to-one relationship with the CPU. That is, every line of code we write in a low-level language translates into exactly one thing the CPU knows how to do, as opposed to high-level languages. Every line of code we write translates into a bunch of stuff the CPU does. All right, so hopefully I see everybody walking around the halls with your white belts. And I will see everybody on Friday. Don't forget your last paper before our programming stuff is due on Friday.